Hi there. Hi. Welcome to your lesson on function notation. Right here, we see a fine example of function notation. Typically, we see equations written as y equals something with x here, but here we have f of x. This is function notation. Notice here, this is the input. Notice here, the name of the function, and we have our output. Let's take a closer look. So first of all, let's say we have this equation and this equation. And somebody says x equals 3. What is y equal to? So you're wondering, do I put 3 in here or here? What do you think? Is the answer 11 or is it 3? Well, it is uncertain. We don't know if this x is supposed to be input into this function or this equation or this one. So we're not sure. Function notation helps to alleviate this issue. Okay, for example, this equation can be rewritten as f of x equals 2x plus 5. So we've called this equation a function now, and we've taken the second equation and named it a function as well, g of x in this case. We can use f of x, g of x, h of x, I of x, anything we want, and not even x, any letters. We'll see that soon. But now it is more clear when somebody says something, because instead of writing, tell me what happens when x equals 3, we use function notation like this. We say f of 3. That means when the input is 3, so when the x is 3, what does the function produce? Okay, when the input of 3 goes into the f function, what do we get? So in this case, this tells us clearly that we're putting the 3 into this function, and our answer is 11. Over here, we could say g of 3. So again, instead of x equals 3, we write g of 3. That means the input of 3 goes into the g function. What do we get? Well, in this case, we get 3. It's more clear here what we're looking for, and function notation was designed for that reason. Okay. Now, let's look at another example of that. Let's say we had this example. Evaluate when x equals 5. Here we have xy notation, our normal equation here, y and x. Okay, x equals 5. Well, in this case, when x equals 5, we simply rewrite the equation, replace the x with 5, and we solve for y, right? In this case, 13. Now, if we use function notation for this is just to highlight the differences again. We would begin by writing the equation as a function here. So instead of y, we write f of x. And then we write f of 5, because 5 is our input, and we get the same answer. The point is it's the same answer, but there's something more to function notation, or more useful as a result than what we discussed already. And that is, let's say you didn't see any of this, and all you saw was this. In this final statement, we see both the input and the output, and that is a small but important advantage of function notation. Here, we just see an answer, and we have to look back on what the input was. In function notation, again, the final step here can clearly show with an input of 5, we get the output. That's a good power of functions. So try it here. Here's the function we saw in that opening introductory slide. Tell me what f of 2 would be for this function. Well, f of 2 means the input of 2 goes in. So 2 goes in here. 3 times 2 plus 1, 7. Okay, how about f of negative 4? Now the input of negative 4 goes in for x. What do you get? This time, negative 4 replaces x. We get an answer of 11. Great. That's using function notation. So try here as well. Here we see a mapping diagram. The inputs are here. The outputs are here. Sorry it's so blurry. But we are looking for f of 2. What happens? The answer is 3. It tells us here the input is 2, goes into the function. What is the output? 3. Input of 2, output 3. Next, f of 3. f of 3 is 3 as well, because the input is 3. We get an output of 3. Okay, how about if f of x equals 1, then x equals blank. This time, we don't know what the input is. See, the input is unknown. But we say the output equals, right? When the function equals something, the output is 1. So what is the input, okay? The output is 1. What is the input? Well, in this case, 5. We can see the output of 1. We trace it back. The input of 5. So we could say, in here, we could say f of 5 equals 1. Great. How about looking at it graphically? Okay, same thing. Here's a function, g of x, and it's graphed here. Now we're looking for g of 2. So the input, or x value, is 2. What's the output, the y value? All right, I hope you came up with 2 as well, because here's our function, here's our x values. So here's an input of 2. I look at the graph. Okay, when 2 is put into the function, the output value is also 2. Right here. Okay, how about g of negative 1? What happens when the input is negative 1? In this case, 0.5, let's check. So again, the input is -1. So I look at the x-axis, go to -1 here, I look at the function. So when I have -1, the output, the y value is 0.5. Okay, if g of x is -1, then what is x? So now we're doing this thing where we flip it around again, right? We're saying the output is -1. What would the input be? I hope you came up with -3. Okay, so now you're looking at the graph and you're like, the output is -1. So now I'm looking at the y values and the -1 here, and I go to the graph. Okay, so that point is at -3, -1. So the input had to be -3 to produce -1. Awesome, so try this one here. Consider this function, find the value of f of 2. F of 2, okay, and also find the value of when x is -1. So it says find the image, right? The image means when, again, when you put this input in, what's the output? So looking for both of those. F of 2 is 5, and f of -1 is 2. Okay, how about this? Determine whether this point lies on the graph of the function. So you're going to check if this input-output value here works with this function. So try this input and see if you get this output. Okay, checking your work here. It works. When you put the input of 5 in there, the result is 26. So that means 526 must be a point. Excellent. How about this? Moving ahead with functions a little bit, we've been using f of x, g of x so far, but the main power of functions is beyond that, that we can name equations or relationships between things using any letters we want, letters that make sense in context. So we've said y equals f of x. In that situation, x is said to be the independent variable, the input, right? Y is the dependent variable. So we can use different variables, and names can be used, such as d equals v of t, m equals c of n, etc. Let's take a look at that in a little more detail in this table. Let's say we have a relation between money being made and shoes sold. So this is like, let's say somebody who works in the shoe store, and the more they sell, the more shoes they sell, the more money they make. So what's the dependent variable here? What's the one that depends on the other one happening? Well, the dependent one is m, money, right? The money you make depends on how many shoes you sell. So the independent variable is shoes you sell. So the function notation for this could be m of s, right? The money you made dependent on the input shoes sold. So again, x value, y value. Do the same thing for here. Hours spent studying and marks you get. In this case, dependent, the marks you get depends on the independent variable, the hours you study. So the function notation could be m of h. Yeah, the marks you get dependent on the input of hours you study. How about this? The ozone layer depth and skin cancer cases. We know when the ozone layer is thinner, there are more cases of skin cancer. So let's see if you can set this up. S, O, and S of O. Okay. The function notation, skin cancer cases dependent on the input of the ozone layer depth. That would be our function. Last one, number of college courses completed and the salary a person makes. Apparently, if you study more and go to college, you get more degrees, you make more money. Let's see. So salary, which is dependent on college courses, and therefore S of C, salary based on input of college courses that you've completed. Okay, that's a little bit just to get us thinking about independent, dependent variables, and also the idea of function notation taking on any letters we want, and the letters can have meaning in the context of the problem, right? So let's look at this one. We have the price in dollars of a motorcycle, T years after purchase, and it is modeled by this function here. So we can see price based on time, price based on time after purchase, right? So there's our function notation, and that means our input, our x value is t, so we can see t over here in this function. All right, and we can see this goes t values from 0 to 6. That means this function only works for 0 years after you bought the motorcycle up to and including 6 years after you bought the motorcycle. After that, this function doesn't apply in terms of telling you the price or value of the motorcycle. So state the independent variable and the dependent variable, and then find the value of p of 0. Okay, let's check. So the independent variable is time, and the dependent variable is price. We can see that price depending on time, right? And p of 0, so you just put 0 in for t. That means your input becomes 0. Put 0 here, and that means 15,000 because this whole thing here becomes 0. So that it says interpret it, that represents the price of the motorcycle at purchase, right? If the time is 0, that means 0 years after purchase. No time has passed. That means the 15,000 must be the original price you bought the motorcycle at. Okay, let's continue the same problem. Find the price after 1.5 years, and then find the value of t for which the price is this. So here it tells you how many years. You're told the input. Here it tells you what is the price. So you're told what is the output, and you're looking for the input. Try it. Okay, so in the first one, we put 1.5 into the function, right? That's our input. 1.5 years goes in, and we get a price of 11,250 out. Great, so 1.5 years after purchase, the price or value of it has gone down already. All right, next one. We're told the value, so we're told the price, and we solve backwards, right? We write our function, we set it equal to that value, and we basically solve backwards for t to find out when will the price be that. Using algebra, solving backwards, you should come up with 3.5. Hope you came up with that. Check your work if you did not. 2 more questions related to this. We have comment on the case t equals 6. What happens when t is 6? And then sketch a graph. Okay, let's try. So commenting on that, well, first of all, when you put p of 6 in, you notice you get 0. So that means after 6 years, apparently the motorcycle has no value. And that's kind of why this says this function only works from 0 to 6, because after that, apparently it will have a negative value, and that's not true. Even a 0 value is not true. You can always sell a car or motorcycle for something, right? Anyway, now sketching the graph. Well, we have the domain 0 to 6. We have a linear function. You can use your calculator to graph this, and we did this in a previous lesson, but you have your domain, so you're only going to graph from 0 to 6, and you already found out what the price is at 0, and that was 15,000, the starting price. And we found out the price at 6 is 0, so you have these coordinates. You know that one x value of 0 produces a price of 15, x value of 6 produces a price of 0, so it should be easy to graph. Let's see if you can come up with that. Well, here's that graph, right? Here's price on the dependent axis, time on the independent axis, so price depending on time. Beginning price, 15,000, values going down, and at 6 years, we just found out it has a price of 0. So pretty easy graph to draw. Great job. We will see you soon.